It's hard to explain the engineering marvel. That is the State Route 71 Blackbird, a long-range plane capable of flying 26 kilometers above the surface of the planet, so high that the pilots could see the curvature on the planet and the inky black of space from their cockpits. It flew so fast that the engineers had to develop entirely new materials and designs to mitigate and dissipate the heat generated from aerodynamic friction. Entirely unique engines were needed to function from zero all the way up to Mach 3.2, dealing with a myriad of problems like cooling, fuel efficiency, and supersonic shock waves interfering with airflow. A plane so advanced that when it detected a surface-to-air missile, its response was simply to change course and speed up. Even though the missiles had a higher top speed, they couldn't achieve the range and high altitude maneuverability the Blackbird could. This allowed the State Route 71 to run hundreds of missions through Vietnam, North Korea, and Iraq without ever losing an aircraft to enemy fire despite multiple attempts. The entire plane was built around the propulsion system, which alone was a miracle of engineering design. For one, no turbine-driven jet engine can operate with supersonic flow at its inlet. Yet this plane was powered by the Pratt and Whitney J58 turbojet engine, but get this, off the shelf these engines could only provide 17.6% of the thrust required for Mach 3.2 flight, a speed at which the State Route 71 could cruise at for extended periods of time. How on earth did it manage that? In order to achieve those kinds of speeds, a ramjet is typically needed. A ramjet, as you can probably guess from the name, relies on ram pressure to operate. Ram pressure is simply the pressure that occurs as a plane rams itself through the air. So as the engine moves through the sky, it funnels this high-pressure air inside. Before entering the combustion chamber, the supersonic airflow must first be slowed down. This basically acts like the compressor stage of a normal jet engine, elevating the air pressure before it enters the combustion chamber. Once the air enters the combustion chamber, it is mixed with fuel and ignited. It expands and accelerates once again out of the exit nozzle. With no moving parts, this type of engine is capable of flying at speeds far greater than a typical turbine-driven engine. But it cannot start from zero. It needs forward movement in order to achieve the correct compression of air in the combustion chamber. So, they are either dropped from a conventional plane, have a secondary propulsion system, or are a hybrid of a conventional jet engine and a ramjet, which is precisely what the State Route 71 used. The turbojet J58 engine of the State Route 71 is nestled inside the nacelle here. In front and around the J58 is a complicated system of airflow management. These control mechanisms allow the propulsion system to transition from a primarily turbojet engine to a ramjet engine in mid-flight. First, the inlet spike. It is capable of moving forward and back by 0.66 meters. This adjusts the inlet and the throat area, which controls the airflow entering the engine. It also keeps the position of the normal shock wave at its ideal position between the inlet throat and the compressor. This is the most efficient position for the shock wave, as it minimizes the energy loss due to drag as air flows over the shock wave. The inlet spike stays in the forward position until Mach 1.6. After this point, it begins to move backwards by 41 millimeters for every 0.1 increase in Mach number, keeping the shock wave in its ideal position. The inlet spike contains perforations which connect to the outside of the nacelle through ducts. Initially, the flow of air will come from the outside in to provide additional airflow to the turbojet engines, but once the plane hits about Mach 0.5, this airflow reverses. As the plane speeds up, the inlet spike develops a significant boundary layer of air. A boundary layer is a layer of very slow-moving air that clings to the surface of objects. By bleeding this layer of slow-moving air off to the inlet spike, it frees up a greater area of the inlet area for high-energy fast-moving air, and thus improves efficiency. Around the engine there is a bypass area, which takes air from the inlet and bypasses it around the J58 engine. This air was used to cool the J-58, which again improved engine efficiency and allowed the plane to fly faster. After the air passes the engine, it rejoins the airflow just after the engine afterburner, adding additional thrust as more oxygen becomes available for combustion and increases the pressure through the ejector nozzle. Air got into this bypass area in a number of ways. There was a shock trap, otherwise known as the cowl bleed, located here, which again helped minimize boundary layer growth. There were suck-in doors located here, which opened only from Mach 0 to Mach 0.5 to add additional air to the bypass for engine cooling. Air from the aft bypass doors located just before the J-58 inlet also fed into the bypass. These, together with the forward bypass doors, which vented to the atmosphere, were used to control the pressure level in the inlet at the optimum level. If it was getting too high, a pressure sensor would trigger the forward bypass doors to open, allowing more air to exit the inlet, while the aft bypass doors were controlled by the pilot. These doors played a critical role in maintaining the position of the normal shockwave. If this was mismanaged, the engine would lose control of the normal shockwave and may even spit it out of the intake, resulting in sudden power loss called an unstart, which would cause the plane to violently yaw in the direction of the faulty engine. If this happened, the forward bypass doors would open fully and the spike would move to the forward to reduce back pressure and get the shockwave back to its normal position. Besides this bypass area that took air from the inlet and dumped it into the ejector, there were also 6 bypass ducts that took air from the compressor and dumped it directly into the afterburner. These ducts were the primary mechanism that transformed the engine from a turbojet into a ramjet. Afterburners are great, they significantly add to thrust without needing a whole lot of additional weight. They basically just inject fuel into the exhaust of a jet engine and ignite it with whatever oxygen is left to provide additional expansion and therefore thrust, but they are really inefficient. However, as the speed increases, they are the only feasible way to generate thrust, and they do gain efficiency thanks to the forward motion, providing the compression of air needed to run them instead of the turbine needing to be powered to turn the compressor stage. The crazy thing about the State Route 71, however, is that the engineers could have eked out more thrust from this engine to increase the top speed even more. Ramjets can go up to Mach 5. So why did they stop at 3.2 Mach? Would they have run out of fuel? Fuel efficiency, in terms of cost, doesn't mean a whole lot to a military plane like this. The military doesn't care about cost. But the more fuel you carry, the heavier and bigger the plane gets, increasing the fuel it uses. There is a break-even point and the plane's range will be limited, but the engineers did manage to fill the plane up with an astounding amount of fuel with some clever engineering. The plane was strictly a surveillance plane, so no internal volume was used for weapons, freeing up space for fuel. You have probably heard that the State Route 71 leaks fuel on the runway because there were gaps in the fuselage. But that's a simple fact that ignores much of the engineering that caused it. The State Route 71 used something called a total wet wing fuel tank system, which meant that the fuel was not contained within a separate fuel bladder. This was a weight-saving measure. Separate metal fuel tanks would add too much weight, and lighter plastic ones would melt from the intense heat generated from the aerodynamic friction. So, the fuel was contained by the skin of the plane itself. The engineers applied sealant to every gap the fuel could possibly come out of, but because the titanium skin of the plane expanded and contracted with every flight, it gradually deteriorated over time, allowing fuel to leak out. Because of this, the State Route 71 had to regularly go into maintenance and have sealant reapplied, but it usually just came back still leaking, just not quite as much. The number of man-hours required to reduce it to 0 was simply too great to fit between flights, so they just had an allowable fuel leak limit, which looked like this. This plane, like a rocket, was actually mostly fuel. Its dry weight, depending on sensor payload, was between 25 tons and 27 tons. Its wet weight was 61 to 63 tons. making it by weight 59% fuel to feed those hungry engines. Even then, without the ability to refuel in the air, this plane would have had a terrible range for what was supposed to be a long-range spy plane. Range varied greatly. For example, the engines became significantly less efficient when the outside temperatures were higher. A fully loaded state Route 71 could expect to burn nearly 13 metric tons of fuel, accelerating from Mach 1.25 at 30,000 feet to Mach 3.0 at 70,000 feet if the outside temperature was 10 degrees Celsius above standard. That's 36% of its fuel capacity. If it was 10 degrees below standard, the fuel burn nearly half to 7.2 tons. Page 26 of 2. And of course the range was severely affected by their speed and use of the afterburner, but on average the state Route 71 had a range of about 5,200 kilometers. Page 27. About enough for a one-way trip from New York to London. Not terribly useful. The US was not going to be landing at their target to hand over a top secret plane to the enemy. However, with aerial refueling the plane could stay in the air more or less indefinitely provided there were no mechanical issues. Really, the range ended up being entirely determined by the pilots. The longest operational sortie occurred in 1987 when the U.S. flew the state Route 71 from Okinawa to observe developments in the Iran-Iraq War. This mission lasted 11.2 hours and likely required at least 5 aerial refuelings along the way. So, if it wasn't the fuel or engines that limited the SR-71's top speed, what did? At Mach 3.2, the nose of the state Route 71 reached 300 degrees Celsius, while the engine nacelles could reach 306 at the front and 649 at the back. This is what truly limited the top speed of the state Route 71. Without careful material selection and design, the plane would simply overheat and fail. Even the fuel needed to be specially formulated to get around these overheating issues. It was a specially formulated fuel called JP7, which had very low volatility with a high flash point. This was needed partially because the fuel leaked on the runway and they needed a fuel that wouldn't ignite easily or evaporate and make the ground crew ill, but mostly they needed a fuel that wouldn't vaporize in the tanks and cause fuel feed and pressurization problems. The JP7 fuel was so stable that it actually doubled as a coolant for the entire plane. The fuel was pumped around the airframe to cool critical components like the engine oil, hydraulic systems, and control electronics. When the fuel got too hot, it was simply sent to the engines for combustion. The fuel was so stable that the plane actually needed to carry triethylborane, a fuel that spontaneously ignites in the presence of oxygen, to start the combustion cycle and afterburners. The plane usually only carried about 16 shots of this, so the pilots needed to manage them carefully, particularly when slowing down for refueling or managing unstarts. One huge question I had about the state Route 71 was why it was painted black. Airliners are all white to reflect heat and prevent the plane from overheating. If that applies to an airliner, why not the state Route 71? The SR-71's predecessors were unpainted, which saved weight, and the areas exposed to the highest temperatures were painted black. Why was this? Surely black would absorb more heat. The Concorde was once painted blue for a Pepsi ad campaign and had to lower its speed as it absorbed too much heat from the sun. However, the Concorde did not fly nearly as high or as fast as the state Route 71, and as the state Route 71 rose, the energy it absorbed from the sun dwindled in comparison to the heat it gained from aerodynamic friction. For this we have to refer to something called the Kirchhoff's rule of radiation, which tells us that a good heat absorber, like a black object, is also an equally effective heat emitter. So the black paint helped the state Route 71 radiate heat away from the plane, as it allowed the plane to radiate more heat. Then it gained it from radiation from the sun. These efforts helped keep the plane cool, but the structure of the plane still needed to be incredibly heat stable. Aluminium is typically the material aircraft engineers turn to. It was used for the Concorde, but as we saw it too had its speed limited by heat to a much lower Mach 2. Aluminium is cheap, has a great strength-to-weight ratio, and is easily machinable. Titanium, the material that made up 93% of the State Route 71, has only one of these properties, its strength-to-weight ratio, otherwise known as specific strength, is fantastic. But titanium is incredibly expensive despite it being the 7th most common metal in Earth's crust. The refinement process is incredibly long and requires expensive consumables. It's also not easily machinable as it readily reacts with air when welding or forging, becoming brittle. For these reasons, titanium is rarely used in structural parts in aviation. However, the real benefit of titanium is its ability to resist heat. The reasons for this are complex that we will explore in depth in future. However, the gist is that titanium alloys have incredibly strong bonding within its crystal lattice that resist heat from breaking them apart. Titanium alloys can resist temperatures up to 600 degrees Celsius before their atoms begin to diffuse and slide over each other, significantly allowing it to retain much of its strength even at 300 degrees. Also has a very low thermal expansion, so that expansion and contraction we mentioned earlier is minimized, reducing the thermal stresses in the aircraft. But titanium too has its limits, and for the State Route 71 this was about 3.2 Mach. Today engineers have made huge strides in material science. The State Route 71 used heat-resistant composite materials as radar-absorbing wedges between the structural frame located in these locations. The manufacturing techniques needed to make composite materials as load-bearing structures did not yet exist, but that has changed. The SR-71's successor, the State Route 72, which is now in development, will take advantage of new high-performance composites, which will allow it to reach speeds up to Mach 6. Many of its engine components will likely be 3D printed titanium with cooling ducts printed right into the part. Its range also won't be determined by pilots, as it will be an autonomous drone. The insane engineering that makes planes like this possible fascinates me, and I recently watched an excellent documentary on CuriosityStream that details the build process for the world's largest airliner, the A380, chronicling the massive sheet metal cutting machines that cut the aluminium skin, the vacuum molds that form it, and the biggest oven in Britain that locks the shape in place. This is just one step in the process, and the documentary is nearly an hour long. This is just one of thousands of documentaries by award-winning filmmakers available on CuriosityStream right now, and a subscription costs just $11.99 for an entire year. With that subscription, you will also get free access to Nebula, the streaming service created by me and my fellow YouTube creators. Here you can watch my Logistics of D-Day series that details the planning and technology that made D-Day possible. The first episode is available for free on this channel if you would like a taste of what you are signing up for. By signing up to CuriosityStream and Nebula, you will be helping not just me, but the entire educational community as we work together to build a place where we can create unique experimental series like Tom Scott's new game show Money. As always, thanks for watching, and thank you to all my Patreon supporters. If you would like to see more from me, the links to my Instagram, Twitter, subreddit, and Discord server are below.